Hey, welcome to episode number 189, in which we are going to talk a bit more about the Cluster API stuff. We're going to jump into kind of the fun part that I discovered while in the intervening time since that last episode. Pretty fun stuff. I found some pretty neat things. I'm going to kind of walk through them with you. Should be fun stuff. All right, what I wanted to show first is, of course, the news, as always. If you're out there, go ahead and say hello. It's always good to know that you're out there. So the latest newsletter, you can go to cilium.io/newsletter to see the latest newsletter. Lots of good stuff happening. Software Engineering Daily Podcast, Byte engineers share how they were applying this philosophy, which is instead of pulling functionality into user space, it makes monolithic kernel dynamic. It allows behavior to define runtime loadable, auditable programs, which is like really very cool stuff. Mr. Tony, good to see you. Talking about how eBPF basically allows you to kind of like really bring a lot more functionality to the kernel, which is pretty wild, which was, originally kind of thought of in the way that microkernel was thought of. Got some good stuff in the technical offering. We got like how to find eBPF helper functions. If you're not aware of eBPF helper functions, think of them a little bit like macros when you're writing those eBPF programs that are going to be injected into the kernel. These are ways of actually like kind of referring to data or referring to context that may not be where you don't have to actually reinvent the whole world, right? Like you can leverage a macro for these things, which is pretty cool. So like determining the container ID or the ID of a process and what namespace it's in, and like these sorts of things. Kind of think of those as like macros. This is a new one to me. Replacing procfs with BPF on a Linux system with around 10,000 processes. BPF is 100 times faster. That's pretty cool. And then of course there's the more work happening in the Netkit world. If you're not familiar with Netkit already, Netkit is kind of a new eBPF based replacement for things like veth pairing and that sort of stuff. Pretty cool. Building eBPF U probes for GPU monitoring. Lots of good stuff in here today. Talking about real-time file system monitoring with eBPF, TCP in UDP tunneling, which is a wild thing. Let's see what else we got here. CB enforces policy access control on eBPF. Interesting. From a three-letter agency. Caracal makes your program stealthier with eBPF. Interesting. And the ecosystem. Bright Future has eBPF. Observability engineering with Cilium. There's a new book out, Magic in the Cloud Native Journey with Hubble and Tetragon. And then the how-to, I saw this one and I was actually pretty interested in it. I haven't dug in too deep, but it's from Christian Cadeau. And the idea is leveraging Cilium and network policies to kind of define a more reasonable security implementation of a multi-tenant environment. Kabir, good to see you. Mr. Daspata, good to see you, sir. So some examples of this in the network governance side, and then the Kubernetes cluster side: managed clusters, managed control plane, managed cluster control plane, Cilium network policies, and Cilium cluster-wide network policies. The implementation uses the following. So kind of similar to what we're doing here, where we're actually, like in this episode, we're going to be exploring a bit more with Cluster API. So like your management cluster, this cluster over here could actually be the namespace in this particular regard. But the way it's described is as a cluster, managed cluster control plane. So managed clusters, tenants share the clusters and are not allowed to create cluster-wide resources. They are not allowed to create or update CMPs. The CMPs are used by the platform to enforce network governance. Cilium does in fact support tiered network policies. This is a new thing, but it can do that now. Tenants cannot directly create namespaces. These are cluster-wide resources, but they can request namespaces from the governance, and MCCP will create the namespaces accordingly. Every namespace created by MCCP include the tenant name as the case label. This label is going to be the important part. On the control plane, the ingress access, network governance allocates CIDRs to new tenants to be used by load balancer services within that tenant's case namespaces, plural. So you have one load balancer pool associated with that entire set of namespaces by label. Cilium CMPs and CCMPs are automatically created for each namespace. There's the load balancer IP pool, and then there's the IO Kubernetes service namespace. You can actually match on the label in it as opposed to, I mean, you kind of are here, but in this case, you're matching on the name of it as opposed to like the label associated with the namespace. Either way, it would work. Default deny, block all traffic except DNS, KubeAPI, and Envoy. Which works. And then segment policies allow pods of the same tenant communication with each other when they are on compatible segments. The names of 3 segments, public, private, and protected, are arbitrary. Interesting. So that's tenant 1. And again, in this case, they're actually matching on namespace labels, like I was describing above. This is an interesting write-up. It's an interesting way of solving this problem. There was a problem I thought, like in the back end, that I was a little confused by, which was, I think it was here, the from CIDR piece. So with this idea, the from CIDR has to, the CIDR has to not be lost in transition from the outside world into the pod. And I'm not sure that that's true in this case, because the IP address of the application when coming into the cluster is actually then going to be natted out over Cilium's internal ingress port. And so I like this part here, from ingress. And so I believe these are, I believe this is an or, not an and. So it would allow from CIDR from the subnet or from entities ingress, which means that you don't have provenance for like what's actually being allowed in, which is interesting stuff. But this is a really cool write-up and a really cool idea. Lots of stuff coming up. Cilium Con, November 10th in Atlanta. We're also in the process of doing Kubernetes Summer School. We just did the first one, and it was pretty well received. We have 3 more left. If you're interested in signing up for them, you can go to isovalent.com/events. And in the summer school, we're going to break it down across a variety of different topics. But it's all traffic in, traffic out, and all about kind of stuff. So session 2 here is going to be talking about Gateway API. Session 3 is going to be talking about load balancer gateway, Hubble, and egress gateway, or Hubble, seeing all your data within the cluster. And session 4 is egress gateway, managing data out of your cluster. So lots of good stuff in there. A couple of KCDs coming up. Container Day Conference, KubeCon North America, of course, November 10th. Lots of good stuff coming up here. So that's our news. Let's jump into what we're going to do today. So today I've made some changes to the way that this is all brought up, and I want to kind of talk through them. But it's all pretty associated with what I was doing in episode 187. And if you haven't seen episode 187, you should check it out. I will copy the link and put it into the chat, as I always do. If you go to this link, you're going to see that video from 187 right here at the top. And then 188 is the one, or 189 is the one we're in right now. So if you want to watch how we got to where we are, that's the video to watch. And I'm going to pick it up with basically like a lot of that already defined. And then we're going to kind of jump into like what I wanted to cover today. So the clusters that I have stood up right now, because I want to kind of walk through this process with you guys. Talk through the meshes. But our goal today is to bring up a couple of KubeVirt clusters. How's it going, Vince? I'm good to see you. Welcome. We're going to bring up a couple of KubeVirt clusters using Cluster API KubeVirt. We're going to configure them so that they don't have overlapping pod sliders. We're going to bring those guys up with Cilium and with a shared CA, because we want the same CA in both clusters. Since we're also going to be doing Cluster API, we're going to be doing Cluster Mesh. We're going to be basically meshing these two clusters together and kind of exploring what that allows us to do and what that means. So if you haven't seen it, you could go here to understand a little bit more about Cluster Mesh. If you go to docs.cilium.io, you go to Cluster Mesh, multi-cluster mesh. So this is a description of what it is. Cluster Mesh extends the networking path across multiple clusters that allow endpoints in all clusters to communicate while providing full policy enforcement. Load balancing is available via Kubernetes annotations. Then we can jump into setting up Cluster Mesh. Now, what we're going to do here is we're going to just basically kind of use a Cilium CLI for a lot of the configuration options here. But we have also enabled encapsulation for the clusters. And then I also got pretty far with the idea of leveraging cluster resource sets to do the install of Cilium. So I kind of want to walk through that. So here's the example of specifying the cluster name and ID. We've already done that. I'm going to show you how we did that. I'm also going to show you how we did that. And then we're going to enable cluster mesh, and then we're going to connect it. And then we're going to talk about like how all of this works in a cluster API context, which should be a pretty interesting episode, in my opinion. So first things first, I have a cluster API control plane cluster up. And that means that what I have inside of here is basically the KubeVirt controller and handler stuff. And then I have Cilium installed as the CNI. And just as before, I also went ahead and created get svc-a. I created a load balancer here, right? So if I do kubectl create, oh, that's interesting. Delete lb. Just realized I have something hanging out in the namespace that was from before that is trash. So if I just create a deployment here, kubectl create deployment echo equals and echo server port 80, kubectl expose go. So I've just created a dumb little deployment with an app. And you can see that that echo server now gets an external IP. And if I curl it, on the correct port, then I can actually talk to that echo server. Right? And that is all happening via L2 right now. So that's a layer 2 load balancer, which means it's picking a node it's picking a node and exposing that node via a layer 2 announcement. And we can even see that the current holder of that lease for the layer 2 announcement is CAPI Worker 2. So CAPI Worker 2 is currently sending an ARP out saying, hey, if you're trying to get to 192.168.200.0, then come to me. Now, you can kind of already see the challenges with this, right? It's like the benefit of this is that we do have a load balancer, a service of type load balancer inside of Kubernetes, which by default is not satisfied by Kubernetes. We're satisfying that with Cilium. But the way that I've got it set up, I'm actually just leveraging L2, which means that if the node were to go away, it might take a second for the for another node to pick up this lease and start announcing that load balancer. So that's one challenge of the L2 component, is that like if the node goes away or something else bad happens to that node, then you might actually see some delay before the load balancer comes back up, which makes it great for the stuff that I'm doing here with like a lab, but maybe not so great for production environments. And that's why we do also have the solution of leveraging BGP. I'm just not showing you that here. Is there something you need to do to get L2? So, I mean, it's all documented in the L2 side of the docs.cilium.io, like how to get it work. But at a high level, basically what's happening here, all I've done, I can actually show you the way that I brought this cluster up, and it's actually documented in the, it's documented here in the chat, in the docs here. Like this is actually the cluster YAML for the kind cluster that I created. And then you can also see like the configuration of Cilium right up here. So enabling L2 announcements and enabling socket LB host namespace only true. And then just down below here, defining the Cilium L2 announcement policy, and then also defining the Cilium load balancer pool. Now, because this is L2, it was important that this CIDR 172.18.200 be in the same CIDR, be in the same allocation as the nodes themselves, right? So if I go back over here and I do kubectl get nodes -o wide, you can see that the nodes are part of 172.18.0/16 because they're part of that Docker network, right? So Docker net list go Docker ls. Right, and so that's part of the kind cluster, part of the kind network, and the kind network is a huge one. It's a 172.18/16. Docker net inspect kind. Right, we can see that the whole subnet for that network is 172.0.0.16, and Docker lives pretty well within its means, so it kind of does it sequentially. It gives out new IP addresses mostly sequentially by the time that they come up, not by the time they were created. And so, so what I've done is I've just taken the 200 block of that, right? 172.18.200.0/24, and I've given that as my load balancer pool. That's what you see up here, right? 172.18.200.0/24. And I'm going to use that 200.0 as that 24 as all of the load balancers for this cluster. So that's one thing to keep in mind if you're going to enable this functionality. That's one of the things you have to do. If you want to enable BGP, you can actually go back to a previous episode and kind of understand how I went about that. Oh, well then, yeah. So if it's the OS firewall, then you would have to enable ARP to leave, and you would also have to, which probably is already there. Yeah, that's an interesting one. So if the OS firewall is blocking it, then the question becomes, I guess if you need it enabled, then you're going to need to know what IP addresses could be attracted to those nodes, and then to allow those IP addresses in through the firewall on all nodes where you could where the L2 ARP could actually land. Because what's probably happening is there's an assumption in the firewall that says the configured interfaces are the only ones that are for which we will be accepting traffic. And this isn't really a configured interface, right? Like it's a, so for example, if I jump into Copy Worker 2, we don't see a 172.18.200, right? If I do ARPAN, oh, you know what? I can just do IP and yeah, show. Right, so there's 172.18.200. 0, 201, and 202. Interesting that saying failed. Probably because it's being intercepted by the kernel, so it's not really doesn't really know the. Yeah, we're announcing that out over Copy Worker 2. So I guess probably have to get that. Probably have to get the. Probably would have to pre-configure the network firewall to allow for that. And that would be the interesting part of the challenge, is trying to figure out like what exactly is blocking you. How you doing, Jamal? Good to see you. But let's keep going here. So where I left off was I've got the cluster built. I've got KubeVirt deployed. I've got all that stuff happening. And let's take a look at some of the resources that we're going to deploy here, and we'll play with them a bit. So first things first, I've got a kv1.yaml, and I want to talk through some of the more interesting parts of the configuration here. So the interesting part of the configuration is, by default, what I ran into was that it's actually setting the domain character here, and that would mean that the search path inside of all of the pods is also changed. So I wouldn't recommend changing cluster configuration networking domain. I would leave that alone. And then if you want, you can actually also overwrite the pod cider and the service cider that are going to be made available within the cluster. So pod subnet 10.243 on this side, and then the next one over for KB2 is going to be 10.242. And the pod ciders cannot overlap in open source Cilium. Like, you have to know they have to be unique on each side. And the reason for that is that basically when we set up Cilium Cluster Mesh, we're going to make it so that the pod cider, all of the components consuming the pod cider in KV1, the cluster, will be able to talk to all of the components in KV2, the cluster, which is pretty neat, because it means that pod to pod will be able to communicate back and forth between the two. And I'll show you how all of that works as we get it all set up. We're exposing this as a service of type load balancer. 243. Oh, I probably need to change that there on KV2. So this is going to be 10.242. I'll also have to change it up here. R2. So as I said, so this will bring up the clusters here. And then there's actually a machine deployment being defined here. Replicas 3, which is good. And then if I look at KV1, I think replicas 3 wasn't actually there. machine deployment, replicas. All right, so these two, so this will go ahead and deploy a Kubernetes cluster with 3 machine replicas, operating version 132.4. It will bring up the whole cluster according to how we described it here. There's one other line here that's super interesting, which is this piece here, which says skip phases, add on kubeproxy. This is valuable because what it does is it will not deploy the kubeproxy add-on to the KV1 control plane, because we want to do the kubeproxy part with our own configuration, or with Cilium, I should say. We're going to do that all with Cilium. So that's our entire configuration for the KubeVirt cluster for KV1. I'm going to copy one. And we'll pop over here to the notes, and we'll drop that in here. There we go. So that is the entire configuration of the KV1 cluster. And then let's go grab KV2 real quick, and that way I can put them both up and you'll be able to see both of them. Got KV2.yaml. All right. So that gets both of the two cluster definitions up into the notes that you can see. So let's go ahead and get them brought up. So if we want to enable cluster mesh at the same time, at the later stage between two clusters, has the same pod sliders, it takes some tweaking, then yeah. Is that a limitation with the Envoy proxy? No, it's actually more to do with the fact that there's an overlap, right? So like every node, when learning about the path to sliders in the next cluster over, is already going to have routes that keep that traffic local to the cluster. And what we want to do is we want to enable the node in one cluster to understand that the slider that is available on another node in another cluster is still routable, right? And so if we, the reason for that is that's why we have to have them separate, right? If they overlap, then basically when we're teaching the node in KV1 how to reach KV2, then there's an overlap there in the routing table. It's a great question. It's not a limitation. It has nothing to do with the Envoy proxy. It has all the way to do with IP routing. All right, let's keep going here. So we'll go ahead and bring up our two clusters. We're going to put our two kube configs in here. So this is actually leveraging DRAM again, right? So if I look at my MRC, I'm exposing kube config as one that's here. And that just basically makes it super easy for me to like just move to that kube config. You could even see that my context changed. Now it's KV1 admin. And if I move over to KV2, now KV2 admin. So back to KV1, kubectl get pods-aw. You can see that there is a single node. And if we watch for a sec, we should be able to see the other nodes come in. Let's see if we can get this working here. So you see our machine replicas, we see them scaling up. That's good. -A. Provisioning, provisioning, provisioning. Get nodes. There we go. All right. So we got our two clusters. Isn't this feature reachability of pods on cross nodes enabled by design in Kubernetes? Yes, in the same cluster, Jamal. That is true. Yes. Yeah. So like if we're in the same cluster, if we're in KV1 and a pod is trying to reach a pod on another node within the KV1 cluster, absolutely yes, that's part of the Kubernetes networking design. But what I'm doing is I'm actually enabling pods on the KV1 cluster to talk to pods on the KV2 cluster. And for that, we need Cluster Mesh. Cluster Mesh basically flattens the pod network between two clusters. And there's lots of good outcomes of that, right? If we flatten the pod network between two Kubernetes clusters, we can actually think of a Kubernetes cluster more as a unit of capacity than a domain in which we deploy our applications, because we can deploy some subset of capacity across those units of capacity, because now we have connectivity between all of them. So we don't really have to think of them. And this enables us to think about things in a fundamentally different way when it comes down to like how we're deploying or managing Kubernetes, because the cluster then becomes just a unit of capacity. And if we need to grow it or scale it, we can scale that unit of capacity up or down. And we can also upgrade, change, modify, delete, remove, do all of those things to a unit of capacity with less concern than if we have all of our eggs in that one cluster. We think of that cluster as effectively like just one domain in which we deploy our apps. There's a lot of information, but I hope that makes sense. We're thinking, if you're thinking about it from the perspective of like how an SRE might think of like a failure domain, or then they also think of like capacity in that way. We are doing, yeah, exactly. Yeah. But we're not really doing too much with service mesh at the moment. We're just doing pod-to-pod networking. So now we have our clusters brought up. Our clusters don't have a CNI in them. I'm going to go ahead and apply. Before I do that, I'm going to go into the resources directory here, and I'm going to show you some of the stuff that I've been working on and some of the really cool things I found out that I was not prepared for. So initially, what I was trying to do when we last met, what I was showing you was this stuff here, which I thought was really cool. So if I do KubeVirt, the Cluster API KubeVirt provider, this guy here, and we go into templates, this is where the flavors of a Cluster API cluster leveraging the KubeVirt provider are defined. And there's lots of really great examples in here, like leveraging Flatcar, leveraging Talos, creating this is the one I actually ended up using, which was the LB kubeproxy free YAML. This is the one that I actually ended up deploying. But let's take a look at this Talos Cilium one, and we can see a really novel idea that I'm sure that the Talos folks came up with, which is here, right? So in their control plane config for the Talos provider, there is this idea of config patches, and you can pass config patches in, right? You can say, I want to add a value to cluster network CNI. I want to add if a file to cluster inline manifests, and the content of that file will be this Cilium install file, which basically leverages the Cilium install command to install Cilium directly in. And then we also want to make sure that we add the file, a file that says cluster proxy disabled. And that's actually all very, very cool, but it's very specific to the Talos configuration. And Cluster API supports something very similar to this configuration that's called cluster resource sets, right? So Cluster API, let me search for cluster resource sets. And it's actually GA in Cluster API. And if you want to know more about how it works, the docs here, the Cluster API Enhancement Proposal, CAPE, however you want to call it, is actually here, and it goes through the different stories about how it all works, what the goals were, and it provides some pretty interesting examples of how to make all of this work. Right? So here's a cluster resource set. It's defined in the default namespace. That's its name. It's an apply once model. It will match any cluster with labels CNI equals calico, and then in those it will deploy these two objects, a secret and a config map. Okay? And there's lots of great examples in here of how all of this works. So let's take a look at that from the perspective of what I figured out. So cool. So this is the KV1 cluster resource set. Now this cluster resource set basically is it's called CRS Cilium. It's in the KV1 namespace. This one is specific to KV1 because there's some specifics in the install that I wanted to make sure are specific to this one, right? It will also do a match, but it'll match on CNI equals Cilium. So the label of the cluster needs to be CNI equals Cilium for this to apply. And then it will apply two different resources. One is the Cilium CA seed, and the other one is the Cilium add-on. And the Cilium CA secret is basically just the Cilium CA that I want to share between these two clusters. I've gone ahead and defined it, and I put it into a secret in this object. And then the other interesting thing about this secret is that it is a different type. It's a type add-ons cluster resource set. And then down below, we have a config map, which is doing much the same thing. It's creating a cluster role binding. And this is, I'm not claiming at all that this is secure or reasonable. This is just how it's currently doing it, right? Probably just for ease of use, but the cluster role at the moment is cluster admin because it needs to actually do an installation of a daemon set. And so like this is a lot of permissions, and it certainly isn't secure. It could be tightened up quite a lot more than it is. But fundamentally, this service account needs to have access to be able to do a Helm install of Cilium. And then down below, we define a job. And that job will be called Cilium install in the kube system namespace. And it has some affinity to basically bring it to the control plane node. Not particularly necessary, but it's there. And we define that service. We make sure that service account that we've given above is in use. We grab the Cilium CLI container. These things are actually not necessary. This Kubernetes service host and Kubernetes service port. This is actually a trick that the Talos piece used, because what it was doing is it was actually trying to leverage, this is why it was attracting it to the control plane, was so that it could assume that the API server would be available on the pod IP. And because this is host network true, the pod IP would be the actual IP of that controller node. So pretty clever, not necessary for what I'm doing here, but let's keep going. We have our Cilium install command. I'm setting this one to cluster ID 1, and I'm going ahead and setting the cluster name to KV1. IPAM Kubernetes, kube proxy replacement true, and then this is what I discovered, and it's so cool. So this K service host equals auto. Let's take a look at what that does, because I was like, what? Well, K service host. Reference. Yes. So right there, Kubernetes service host. Use auto for automatic lookup from the cluster info config map. Amazing. So what this does, previously I was trying to figure out like how I would propagate the URL of the API server's load balancer down to the guest cluster. And what I realized is with this configuration, I don't need to do that. This is what that does. This is so cool. So K service host auto. Let's take a look at the config map. So inside this cluster, there'll be one too, right? So kubectl get config maps -n kube public cluster info -OYAML. So here's an example of the cluster info config map that's propagated by Cluster API into the cluster. Right, here's the server name and the port that is used inside of. This is how all of the nodes will build their kubeconfig when trying to generate their certificates, so that those nodes can come and be a part of the kubeADM cluster. If I move into the KV1 cluster, KV1 kubectl, and we look at this one, we can see that it has an IP address of 172.18.201, and there's the certificate authority data for that cluster. And the same thing for KV2. Right, 200.2 and certificate authority data. So what's so cool about this is that this is how Cilium will build its configuration. It will leverage the service account that we created. It will use that service account in combination with this certificate authority data, or perhaps the certificate authority data made already available to the Cilium pod on its file system, and this server FQDN to determine the K8 service post and K8 service port. And in this way, this will basically enable all of the nodes to use that API server directly to interact with the API server, since there's no kube proxy, right? There's no kube proxy in the cluster, which means that we can't rely on the internal representation of the Kubernetes service object. We need to know what the IP address of the API server is, or a usable API server IP address, to kind of allow Cilium to start building the kube proxy capability. And this is how that works. It's so, so cool. So it means that my configuration in the resources is so much easier than what I was trying to do, because I can just say, K8 service host auto, and it will figure it out from that config map specific to the cluster in which it is being installed. That was such a huge revelation to me when I was trying to figure this out the other day. So let's go ahead and get these applied. Here we want kubectl apply -f resources KV1. We'll put that in there. We'll put KV2 in there. Okay, so then kubectl get clusters all show labels. You can see there are no labels associated with the clusters currently. Kubectl label clusters. So what this does is it labels all my clusters CNI Cilium, because why else would I want that? I do cd kv1 kubectl get pos -aw. Whoop, already off and running. So there's our Cilium install command. And we're already adding our Cilium config. Very, very cool. And actually, you know what that's occurring to me? Kubectl log -n kube system Cilium install. I probably could have done like --wait, and that would have given me more output here. But as it is, it's basically just doing an install of Cilium, so that should be fine. Waiting for those guys to come on up. And this means that the cluster, like at this point, I could also like have a CRS that adds Argo or adds Flux or adds any number of things, right? And that CRS would then be how I install the rest of the resources into this cluster, right? It doesn't have to be unique to the cluster. Like, it makes it very easy to bring up like a fully deployed Kubernetes cluster. It is very, very cool. Let's take a look at KV2. Get pods. Yeah, already deployed. We're in good shape. So now we have our two clusters. We're sharing the same Cilium CA between the two. And just to prove that, like here's the MD5 sum of the data component of the Cilium CA. If I move into KV2 or KV1, in that same command, you can see that the CA is the same. So there's lots of ways to solve this problem. What I'm doing here is probably the easiest, right? Because what I'm doing is I'm just taking the CA and I'm predefining it, and I'm using the same CA for both clusters. And that's important because when we build Cluster Mesh, we're going to use that CA to generate the certificates to allow Cluster Mesh to communicate between the two. And because it's the same CA, there's already an established trust between those two. If we want to do this with like, I don't know, we're going to do this with like Cert Manager, for example. I could absolutely do this with Cert Manager. It would just take a little bit more work. I would have to make, and there's actually not even a requirement that the CAs be the same, right? Or the issuers be the same. There could be an issuer on both sides. It's just that when it comes to validating the incoming client certificate in the MTLS model, the incoming client certificate from from KV1 talking to KV2, it needs to have a CA to validate that client certificate against, right? And so in my case, I'm saying the easiest way for me to say all clients and all server certificates are trusted across these two clusters is by sharing a CA, but it's not a requirement that that's how you do it. It's just the simplest way for me. All right, so we got our cluster set up. So let's do this. I'm going to jump into here. I'm going to make dir all. I'm going to fix my editor. Okay. So what this is doing is I'm gonna set the kubeconfig to include 3 different kube configs, and those 3 different kube configs, it's important that they don't overlap. But in my case, I know that they don't. And so what I'm going to do is this will allow me to switch context between the 3. So if I do that, now if I do kubectl get nodes, we can see we're talking to the CAPI cluster, KV1, the KV1 cluster, and the KV2 cluster. And what this does when I use those 3 contexts by path is it basically makes it so now I can use the context command for the rest of the stuff that I'm going to do here to create these clusters. What if you deploy Cert Manager in the host case cluster? See, I could do that, but the challenge is that, there's lots of ways you could do this. I could put the Cert Manager into the CAPI cluster, and then generate from the CAPI cluster a new CA or a new issuer CA, and then populate off of an existing CA, right? So like basically make a secondary CA from that first one, right? So with this one common CA, I make 2 individual CAs, and I put these 2 individual CAs into KV1 and KV2, and then I take that common CA at the top and I make that a part of the trust chain for for each of the other two clusters. And that would actually also work, right? Because you'd still have the certificate that trusted the one that you're trusting in your trust chain. But certificate stuff gets complex. There's lots and lots of ways to skin this cat. I just did it in the easiest way to do it. So let's jump back over to Cluster API Service Mesh or Cluster Mesh. So what I've got right now is I've got the two clusters. I've gone ahead and set their identity. I've gone ahead and done these other pieces here. So the next thing I want to do is I want to take a look at the enable. So we're just going to do Cluster Mesh enable on both sides. So let's go ahead and do that. See, it's pretty small, so let's go like that. And then we'll go like that, and then we'll do Cilium Cluster Mesh and enable dash context KV1 admin KV1. Oh, service type load file. Now this is things are going to get. Actually, just the load port here. Load port. But that will be okay. We'll talk about it here in a minute and describe why that's okay. And we'll do KV2, KV2. We're going to enable both in node port. Now, the reason this warning happens is because it's like if I try to go and talk to that other cluster on that node port and one of the nodes goes away, then I'm actually configuring Cluster Mesh to understand how to reach that node and on that node port. And it might fail and have to come up with another way to get there. If I created a service of type load balancer, then when nodes come and go, it doesn't matter because the load balancer will always work. And that's actually how I'm going to try and connect them. So let's talk a little bit about that and talk about how this works. So at the moment, so actually let's do Cilium Cluster Mesh status context KV1 admin at KV1. So we see cluster access information is available at this. But we can see there's only like the one IP, right? And that's not going to work very well, but that's what we have defined at the moment. So that's what we got set up. Let's go ahead and talk about the next part of this. Now, at the moment, if I'm in the CAPI cluster, which is what I'm looking at here, kind CAPI, if I do kubectl get svc -n kv1, we can see there's a service of type load balancer there. And if we inspect it a little closer, we can see that the load balancer that's being defined is basically pointing at a selector, which is right here. And it's saying, go ahead and point this external VIP 172.200.1 to any node within the cluster name KV1 that has the role control plane, right? And so the benefit of this configuration is that it's going to forward that connection directly into the nodes inside of this cluster that have control plane as their role. And that's how they expose the API server in the configuration here. So if I remember correctly, CAPI have cert manager deployment as part of, yeah, it's true. It is actually in the CAPI cluster currently. Yeah, so if I were feeling smooth, I could probably do that. Yeah, so cluster API is right here. Sorry, cert manager is right here. You could all get issuers, okay, right? And then I have the self-signed issuers. This is why it needs it. It needs a self-signed issuer for the CAPD, and then the kubeADM components, and then the CAPE system and CAPK system components. So it's creating a trust chain for each of these. But I could create another one. I could create another like shared CA issuer, and then create one each of a shared CA issuer CA into each of the two KV1, KV2 namespaces, and then copy that CA issuer down. That would absolutely work. Nothing wrong with that design. All right. So that's how this service is defined. So when you're interacting, when kubekettle is interacting with the cluster, right? If I do kubekettle get, if I do kctx, if I move to KV1, failed to switch context. Cannot determine kube compatible. Oh wow, I didn't know that. Huh. That's funny too, because, well, so here's a little inside weirdness about kubekettle. Let me hide this comment. If I do kubekettle config view, we can see that we have an entirely built up kube config. It's made up of all three kube configs that I combined as path elements. And if I do -o raw, or at --raw, then it would show the entire client key, all that stuff for the whole thing. So now if I go like that and I do kube config, and I edit my DRM, and instead just point to so now if I do kctx, it should let me get away with it just fine. Yeah, that's so odd. I wonder why it cares about the pathing. So what happened there was when I tried to use kctx, it cared that I was actually building my kube config dynamically from path elements instead of just looking at the memory object, which is so interesting because the kctx command, didn't it bash or something? Nope. Let's go. But anyway, the Go object doesn't have to actually look at the path. It can just look at the memory object. So that's confusing. I don't know why that does that. Doesn't matter right now, though. Let's keep moving. So clear. So that's our kube config. So then we are going to kctx. Can I get pods? Okay, so we've got our two clusters set up. We've done our Cilium Cluster Mesh enable. I wanted to create two new services. SVC, actually. kubekettle get SVC -n KV1. We'll grab this one, and we're going to expose our service mesh this way. Our cluster mesh this way. And so before I can do that, though, I need to know where to point it, right? So let's say kubekettle get pods -n context KV1. Okay. So here's our cluster mesh server. I'm actually going to do wide here. Our cluster mesh server is currently on a deployment node. Sorry, a machine deployment node. So there's no built-in thing that keeps it like in a specific control plane worker node kind of thing. It's actually just going to be the one thing that's going to be right there. So now we know. So if we pointed at the control plane, that would still work, but it would actually make it kind of dumb because it would have to jump through. So it doesn't really matter too much, but let's keep going. KV1 mesh. Let's get rid of some stuff we don't care about, and we'll rename it mesh, get rid of the resource in the UID. We don't know any of these things yet. We do know these things. We don't want that. And we'll get rid of status. So let's pop open another terminal here. Copy all. We could actually KCTX KB1. We could all get SBC. So we don't particularly care about the node port. So we're going to just ditch that line. And 379. And our target port is going to be the node port of the inside cluster. So node port will be 32379. So we're going to be exposing it on port 2379. Our target port is going to be the actual node port exposed, which is 32379. And we're going to be sending it to any pod within the cluster name KB1. Should be enough to get us there. Go apply -f, KB1 mesh. Oh, context. Copy. Our service has been created. Kubectl get SBC-n KB1. There's our mesh. Load balance VIP. And there is our load balancer for the API server. All right, so we got that worked out. Let's go ahead and build the one for KB2. So CP KB1 mesh, KB2 mesh. YAML. I'm going to call this one KB2 2. We don't know the port. So let's look it up. Kubectl get KCPL. SBC-n system. KB2. R. Cluster Mesh API server is 32379. Go apply -f KB2. All right, there we go. So now we've got our exposed load balancers. Kubectl get SVC-A. Grep mesh. So there we go, 203 and 204. Those are pointing at two different backends and two different clusters. That's all good. Okay. So let's go ahead and build the next part of this. Let's go ahead and try and do our Cilium Cluster Mesh. Cilium Cluster Mesh connect context destination endpoint is going to be 200.4. And the source endpoint is going to be 200.3. So I believe this will, by default, let's make it a mesh. This should, in my opinion, allow for a cluster mesh connection between context KB1 admin KB1 and destination context KB2 admin KB2 for the destination endpoint of, that's the destination context destination endpoint, 204, source endpoint 203, connection mode mesh. Didn't work. Must be IP port. Okay. We're exposing it on port 2379. Boop! We did it. So now we have cluster mesh configured. Cilium Cluster Mesh status. Context KB1 admin at KB1. There we go. KB Store Mesh is enabled, and we're all configured up. Sweet. Now we do Cilium Cluster Mesh. We do Cilium connectivity test. Multi-cluster. So there's a Cilium connectivity test for multi-cluster. Let's go back to the docs here. I'll show you that. What time is it, by the way? 12:08. Okay. So we did that. We got that all working. We got our connect done. We got our cluster status. Actually, you know what we should do? Before we go into this, I want to look at this real quick. So remember how we did, that's KB1, KB2 admin at KB2. Boop, boop. All right, so we're in good shape both sides. Let's go ahead and run this command. And multi-cluster. And let's see what happens. So we can see what happened here is it went ahead and created in KB1, it created a namespace called Cilium test, and in KB2, it created a namespace called Cilium test. It deployed the echo same node, echo other node, same node deployment, etc. We're just going ahead and validating our connectivity. This little error is basically that I haven't turned on Hubble Relay. Oh, that's okay. So this will actually do all the testing. Probably quite a lot more testing than I need. I wonder if there's a way for me just to focus on just that part. Oh, that's interesting. It's a new command. Cilium DBG troubleshoot cluster mesh. That's cool. I didn't see that before. Let's try that out. Let's open a tab. Get on exec. Dash and system. Yes, Cilium context. We're in the KB1 Cilium pod. Cilium cluster troubleshoot mesh. Neat. That's cool. What's that other command we saw in the troubleshooting? Cilium status all clusters. Status all clusters. Check that out. That's what we're talking about. See here where it says cluster health, we see 8 reachable. That's so cool. That means that all of the nodes are now available for use. We can see all of the nodes are in this map. We get all the Cilium. Work. Nope. Okay. So we have 243 and 242, right? So there's the 242 endpoints in the map, and there's the 243 endpoints in the map. So this is how cluster mesh works. Inside of here, we can see all of the IP addresses of everything in both sides of the cluster. So if I were trying to establish a ping between both sides, I'd be able to do it. If I wanted to expose a service in KB1 and make it available in KB2, I would be able to see all of that. Let's pop back over to our other tab. Things are going well. Don't see too many errors at all. Plugging away. So let's do that real quick. Let's expose a service. I think there's actually even a quick start for this in the docs. So cluster mesh. blah. Got that done. Did those things. Connected the clusters. Let's test code. We're doing that. So there's our global services. So here's an example of load balancing with a global service. Yeah, here's our quick start. So let's deploy a simple example service. Let's do that. In cluster one, deploy this. So it'll apply. Check. Oh, I see. KCTX, give me one. KCTX, KB2. Cluster 2. From either cluster, access the global service. Oh. Dash A. We can see that this is going back and forth between cluster 1 and cluster 2. You'll see replies from both pods. In cluster 1, if you add service Cilium shared false to the existing global service, then from cluster 1, you will only see that one cluster. From cluster 2, exactly the same. Yeah. We got it all built up. Pretty cool stuff. We're most of the way through this test set, so I kind of wanted to let it finish before I jump out and do something else. But I did want to actually share like how to validate all of this stuff because I think it's pretty cool stuff. Oh, actually, now that we've done this, I bet if we do Cilium Cluster Mesh status, we should see one global service. Or I guess we'll see multiple global services. So now we do Cilium bubble port forward. This will be cool. And then we do Hubble observe dash F dash N default. There's no traffic through there. Oh, I guess there's rebel-based traffic happening at the moment. Let's split horizontally. And we can even see just in this output, right? We're seeing traffic coming from 10.234 from this host to this host. So cool. Actually, this would be what if we do display. We see KV1, KV2 going back and forth between these nodes. Full mesh going. Pretty neat stuff. What would it look like if I see? What would it look like if I want to access rebel base from outside of the cluster through service of type LB? Well, at the moment, the way that would work, let's do it. So kubectl get SBC. So there's our rebel base. It's currently a type load of type cluster IP. So source port, target port 80. So that's fine. So we need to change this to service type load type node port. So if I do kubectl edit svc-n rebel base. Right down here where it says cluster IP, I want to change that to node port. Boop. And then we do get service. We can see the node port 31492. And then we'll just copy KV1 mesh to KV1 or KV2 mesh to KV2 rebel. And KV2 rebel. Okay, so we're going to land traffic on port 80. We're going to send it to any node in the cluster, leveraging 31492. Let's ship it. Oh, wait, we got to change the name. Sorry. Because they'll all conflict. So there's our K2 rebel. KCTX. Time copy. kubectl get SVC. Our role endpoint. There you go. That's how that would look. Very neat stuff. Let's see how our testing is doing. Oh, it's all done. We did 71 tests successfully. We saw 41 tests skipped, and that's okay. Cluster entity multi-cluster. Yeah. Super cool. Well, there we did it. We had our two KubeVirt clusters. We have full cluster mesh going. We were able to show Hubble connectivity between things. We've got all the things going on here, and I think that was everything I wanted to show and like kind of describe how all of that works. So I hope that was useful. It was super interesting for me. I especially was really, really impressed with the ability to say to auto detect the API server configuration. So one of the things I learned from this, that even as field CTO of Isovalent, I did not know, was this piece right here, which was right KV1. The custom resource set, when I'm doing the Cilium install, just leveraging the open source Cilium CLI, right here, this K8 service host auto. So cool, because it makes it so much easier. I didn't have to think about like, how am I going to propagate the kubeconfig from the host cluster down to the guest cluster and then make that kubeconfig available inside of this deployment. It's just all I had to do was K8 service auto, and it was able to figure that all out. And that was such a breakthrough, like such a breakthrough when I was looking at this earlier this week, trying to figure out how this would all work. But anyway, it's been a pleasure. I hope you had the best weekend of your life. I am off to have the best weekend of my life, and I'll see you all in a couple weeks. Talk to y'all later.